Let me hit record here. Okay, so what do I have, about a half hour?
Half hour is good, yeah.
Okay, all right. I'll calibrate myself accordingly then. So, um, I have a few windows open here. So this, I should review how to get to this if any of you are wondering. So the link to remember is this dataloggers.live2zero.com, and from there you can get to the monitoring dashboard, the controls interface, and then the Eagle IO interface, which is what we'll spend most of this time looking at. So the monitoring dashboard is useful to have open. If you're not familiar with the system, the looking at these charts in Eagle IO can get a little confusing because it's hard to kind of match up these names with the locations and what's being measured in the physical system. So if you're kind of new to this, then I'd encourage you to also have the what I call the monitoring dashboard open, particularly on the water space heating tab, because you can see a schematic of the system as well as current readings at each of these measurement locations. So I'll probably flip back and forth between this interface and the Eagle IO as we talk here, just to kind of remind you what we're looking at on the charts. And then it's also good to be familiar with this controls interface. So this is what the occupants and I are using to change set points and to turn things on and off. So I'll refer to this also as we go along. So, um, and fortunately, we got lucky. The last 2 days have been really good for illustrating um, kind of classic, spring, fall, shoulder season uh, behavior in the building, um, where there's significant opportunities for energy savings. In the winter, let me open up. Well, actually, let me first start with the typical cold day in the winter and just kind of explain how the charts work, and then when we go back to this spring view here, you'll kind of appreciate how much things have changed. So I'm gonna pick a date in let's say December or January.
I know it was cold.
Yeah. So we're going to look at 7 days worth of data. And I'm looking at the space heating chart right now. All right. So this actually was a pretty mild week in. Oh, wait, this is March. I'm looking at the wrong thing. Hang on. Calendar. Oh, that's what happened. Um, Let me do it this way. 3 months worth of data. Actually, this might take too long to load. This is actually a problem with this interface is that so this space heating chart is something that I pre-configured, and I'm noticing now that it doesn't actually. Oh, here we go. Custom. I thought I just did that though. Bear with me, everyone. January 3rd through January 9th, let's say, and apply that. Up. Okay. Aw, snap. All right, I'm gonna have to report that to the Eagle IO people because that shouldn't happen. You should get like a warning that you're trying to load too much data instead of getting a JavaScript error like that. But let me try that one more time. All right, custom January 3rd. Let me just do a few days. January 6th. All right, that worked. Okay, so here we've got, see what the temperatures are. All right, um, let's see. Yeah, this is good enough. This actually is not that cold. So the purple line is outdoor temperature, and this is Fahrenheit on the left. So it's kind of between 20 and 40 throughout these several days. And let's look at kind of this period right here. So this is pretty typical where we've got, and let me just describe what these lines mean. So the dashed black line here is the temperature set point. So the green line, which is indoor temperature, is, you can see it kind of, it's going up and down a little bit above and a little bit below the set point as the heat turns on and off. And you can see that on this day, which is pretty sunny here, what is this, January 4th, um, this yellow curve represents how much sun there is, the solar radiation. And this is a pretty sunny day. It looks like it's mostly sunny. And you can see that even though the temperature is about 30 here in the middle of the day, the green line is starting to rise above the temperature set point, and that's because the sun is heating up the house. And then it drops down as the sun goes down again, back to the set point, and then the heat has to turn on. So at the bottom here, the gray areas, the gray indicates when the pump that supplies water to the radiant floor is operating. So think of the gray as when the heat is actually on and the space is being heated. The red line indicates when the backup heating element in the solar tank, the tank that heats up the floor, when that backup heating element is on. And so the idea that the way this works is that we have two heat sources for the solar, for both of the tanks. We have one tank for the domestic hot water, which is, for showers and faucets and things like that, and then another tank for space heating. So space heating tank is probably a more accurate way to name this, but there's two heat sources for each of those tanks. They each have a 5 kilowatt, it's roughly 5 kilowatts, electric heating element. So that's just a lot of electricity that's being pumped through this element, and that heats up the tank. But the whole idea here is that you want to limit the amount of time that you rely on that electricity to heat up the tank. Instead, we want to take advantage of our better heat source, which is from the evacuated tube solar collectors on the roof. And so on a sunny day like this, what you see is that the heat turns off at about 9 something in the morning, and soon after that, the red line goes down to 0, which indicates that the electric heating element in the tank turns off. And then a little while later, the brown line, which represents the pump circulating the water through the solar collector. So during this sunny day, the pump, we're collecting free solar heat between about 9:45 and 3:30 or so. And that's kind of this is what a partly sunny or a mostly sunny day looks like. This next day is mostly cloudy, it appears. And the one before it is maybe partly cloudy, or kind of hard to say, partly sunny, something like that. So you'll see that during the winter on these nights, so this night was pretty much down at about 20 the whole night. And we kept the heating set point at 72 the whole night. And that 72 number comes from feedback that I got from Hannah and Jacob, who are the occupants in the building. So after everything started, finally working well, then I kind of went back and forth with them for a couple weeks, and they were telling me when it was too cool and when it was too warm. And it appears that about 72 is about right. And Hannah is actually, she said that she's surprised that she felt cold or cool, let's say, below 72, because she said she keeps her thermostat at home at 68. So there's many reasons why that could be, why she feels like the temperature needs to be warmer in this building compared to her house. It could be the sensors themselves. It could be just the amount of glass that's in the interlock house. There is a lot, so many reasons. So we don't know for sure, but they said they're comfortable at about 72. So what was happening is that if I would turn the temperature down to, let's say, 62 or even 64 or so at night to save energy, what would happen in the middle of the winter is that it takes many hours for the house to heat up again, so that it's back to 72 by the time they show up in the morning. And the reason for that is because this is a high mass system. So instead of when you turn on a furnace with forced air heat, the building heats up very quickly. But the materials in the building may not be that warm, but you're heating the air directly, so people feel comfortable much quicker. But in this building, you have to heat up the whole floor. So you have to raise the temperature of the floor from maybe 60 to 80 before you start to feel the heat in the space. And that can take many, many hours. It was almost taking 6 to 8 hours in some cases. And so what I was finding is that we were turning the temperature down after they left the building for the night, and then soon after that, the heat would have to come right back on. So that's actually an interesting controls problem because you still can save energy by even turning the temperature down for a few hours. But you can see on the controls interface here that the way I set this up is that you have to type in the times that you want to. Essentially, these times here are when you want to have the temperature set point at 72 versus 62. So we're saying here that at 5 a.m. We're saying that the building is occupied and we want to use the occupied set points, which is 72. And then after 7 p.m., we're saying the building's unoccupied and therefore we can go down to 62. So as the outdoor temperature changes, so recently it's been mild, in the middle of the winter it's not, the appropriate start time when we should turn that temperature set point back to 72 could be right now. This time, the past few days, it's only taken a little while for the house to heat back up to 72. First of all, because the heating system is not fighting with the heating load caused by the low outdoor temperatures. And secondly, the building itself is not getting as cool overnight. It's not going all the way down to 62. It's maybe only going down to 67, 68. So the building doesn't have to heat up as much in the morning when you need to get back to 72. So one controls question here, ideally the way this would work is that you would say, okay, well, how long will it take to get the house back to 72? And set your what's called the setback temperature schedule to the appropriate time so that the building has just enough time to get back to 72 degrees. But that's not part of the current algorithm. So that capability is not in there right now. So instead, for simplicity, during the winter, I figured this is also easy to calibrate a model against, is just leaving the set point at 72, not touching it, and then we have a lot of good data through a winter to calibrate the model against. But next winter, we might want to think about trying to optimize things to start, saving energy.
Hey, Mike,
Yes.
I just have a question for you. I don't know if you're gonna know the answer, but so when the system gets shut down to the unoccupied set point and it has to reboot back up to the occupied set point,
Yeah.
does that use more energy than holding it at that set point for the entire night?
Say that again, that last sentence.
Does it use more energy when it has to kick back on than it would just maintaining the temperature throughout the night?
No, that's a myth. That's a widely held myth that the system somehow has to work harder or it's
Okay.
not as efficient. It's actually better. It saves energy for two reasons when you turn it off, when you use the setbacks like we're talking about, and
Yeah.
where it needs several hours. One reason why it's better is because you are letting the difference between the outdoor temperature and the indoor temperature is somewhat smaller when you let the indoor temperature go down. And
Right.
therefore the building needs less heat to warm up, less electricity. And the other benefit is that when the system turns back on, it's staying on continuously, and all mechanical and electrical equipment likes to operate continuously. First of all, it especially not so much this system because it's 100% efficient electric heat. So it's just as efficient when it turns on and off as it is when it stays on all the time. But all mechanical and electrical equipment has a shorter lifetime when you turn it on and off more. So
Interesting.
yeah, so it's good to, and that's why when you design a heating or a cooling system for a building, it's very important that you don't oversize the system. And undersizing it means you may have comfort problems. Oversizing means that the system may fail earlier, it won't be as efficient, and
So
it's
the cost,
also less comfortable because it's turning on and off more. So now this building doesn't have as much issues with during heating season with comfort because radiant floor heating is very comfortable. It's not, it's comfortable from an acoustic standpoint because you don't hear it coming on and off. And it's also, you don't feel the temperature fluctuations as much. Was somebody going to
and
say something?
yeah, for the energy, just for everybody, for the energy consumption, the delta T matters most.
That's the magic number. So it's really, so the when you look at these, at especially this space heating chart, the two variables that drive everything else, the two variables that have the most influence on how much the heat has to turn on and off is delta T, so green line minus purple line, and the yellow chart, which is how much solar there is. Things like wind speed and relative humidity and things like that are secondary effects. They do matter, but you're not going to see them as obviously in a chart like this as you can with delta T and then solar radiation. Those are the dominant contributors. So you can see on this winter night, 20 degrees outside, the gray shaded area, it looks like the heat is it turned on 3 times during the night and turned off so it was off for shorter periods of time than it was on. And it was on for, let's see, this is 10 p.m. through 2 a.m., 4 hours. It took 4 hours for the building to go from 71.5 degrees to 72.5 degrees. And you can see on the chart here that, it's a little hard with the scale, but the temperature is still dropping after the heat turns on, and that's because it takes so long for the floor to heat up, because the floor has cooled down in these previous couple hours, right? And so it takes like an hour for the floor to turn up, for the floor temperature to heat up, and then finally the space starts heating up very slowly. And then it reaches 72.5, which is when I have the heat programmed to turn off. And that's called the dead band. So it turns on at 71.5 and turns off at 72.5. So that's a 1 degree dead band. And that also helps the system, keeps the system from turning on and off too frequently. So that's the story there for a winter night. Okay, so anything else to say about that? And you can see, even though it's cold outside, that the building is heating up to 75, even though it's in the mid 30s outside. And that's because this was a sunny day. On a cloudy day, you could see that that doesn't happen, right? So, and actually the heat had to turn on in the middle of this day. So on a cloudy day, you are getting a little bit of solar contribution, but not much. And so you'll see typically that the amount of time the heat has to turn on reduces during the day, but it's not like it still comes on, whereas during a sunny day, it just doesn't come on at all until the sun goes down. And so when we're talking about the spring and the fall, what we want to be looking at is it's really this early morning, so before the sun comes up and soon after it comes up, where things need to be optimized. So, okay, so that's winter, and then if I go back to the current chart, let me go to here. Let me just flip here.
Good indicator also for Kaling if the temperature, right, that range, that delta T, if that's high, you expect high energy.
Yep. All right, so this is the past 2 days, and this has been a perfect illustration of what happens typically. So I was noticing that as the outdoor temperature started to warm up a bit, the heat was still coming on and off all night, and it's not as and now we're to the point where it doesn't take as many hours for the building to heat back up in the early morning. So I figured it was a good time. I don't want to have to go into this system every 3 times a day and change all this stuff, because that's too much work for operating a house. When you feel like you need to change set points, multiple times a day, that's usually an indication that it's time to improve the control algorithm. So that's what we're talking about today. Um, so what I did is I said, okay, I went from no setback, meaning that I was just keeping the system in manual mode and forcing it to stay at 72 degrees all the time, the set point. But a few days ago, I turned off manual mode, which then allows the system it says, okay, we're okay with 62 degrees between 7 p.m. and 5 a.m. And between 5 a.m. and 7 p.m., we want to stay at 72. So that's why the dotted black line is going up and down here. So you could see at 5 a.m., the set point goes up to 72, and then it drops down to 62 again at 7 p.m. All right, so 2 days ago, what we had happen was that, outdoor temperature, now we're in the 40s, and then it went up to the high 50s during the day. And now the previous day, I think, was really warm. So what happened is that even as the temperature dropped overnight, let's see if we can pull back a little bit. All right. So yeah, you could see outdoor temperature 65 on the previous day. So the building, and also the building was not occupied that day, which means that the occupants never overheated and never opened the windows. So the building was trapping all the heat that it was being collected all day long, and the temperature got really warm inside. So you can see here right at the edge of the chart, 78. I think it made it up to 79 or something. So the building's storing all this heat. It's not being released because the occupants aren't opening the windows. So therefore, as the temperature went down overnight, the temperature slowly went down inside, but it never reached this 70. Well, let's put it this way: at 5 a.m., when the set point went up to 72, the indoor temperature was still above 72. So therefore, the heat never came on in the morning when the set point went back up. But on the next day, today, the occupants were in the building yesterday, and you could see this whenever you see a gradual increase of the green line and then a sudden drop, that almost always indicates that they open the windows. And I'll show you something else that makes that even more clear. So they overheat. They were feeling too warm at about 76. Okay, so they decided to open the windows. That cooled the building down, but it meant that when they went home, when they closed the windows back up, and when the sun went down, the temperature drifted up a little bit, and then it started falling. So by the time we got to 5 a.m., the temperature was 69.7, which is below 72, and therefore the heat came on, as you can see down here at the bottom. And so it came on from 5 a.m. and stayed on through 7:50. So it was on for almost 3 hours. And then what happened is that the building heated up, and here it didn't take too long for it to start heating up. And then it heated up all the way to 72 by 7 a.m., 7:15, which is actually before they even show up, the occupants. So but by the time they got there at 8, the temperature was at 72.8, which means that the building is already heating up from the sun. And then what happened is you see it rises pretty steeply until it gets to 76.5. They got too warm, and then they open the windows, and it drops way down. And then at some point they close the windows, and it's drifting up again, and then it's going to fall back down again like it did this yesterday. Okay. But what the key thing here to realize is that, first of all, think about how much electricity is wasted by having this, the red line again indicates that the backup heating element in the tank is on. And that's because not enough solar was collected during the previous day to provide all the heat that was needed to heat the building up, okay? There was some, usually what happens is in the winter when there's very little solar heat being collected, the red line appears about a half hour after the gray line starts. And that means that the tank is using whatever heat it had left over from yesterday or the previous time it was on, and then the backup heating element has to come on. Here, the pump is running through, the radiant floor pump is running for about an hour before the backup heating element comes on. And that's because for at least an hour, it's running off of the free solar heat that was collected during the previous day. What you'll see when the heat comes on several times at night, the first time it comes on, you can see that it's using a bunch of the solar heat. And then every time after that, there's no solar heat left. Then you're having to use electricity. So the red line jumps up soon after the gray line jumps up. So if the heat was on, so if the backup heating element is on for about, I think it was 2 hours, 6:06 through, okay, 2 hours. So 5 kilowatts continuous for 2 hours is how many kilowatt hours? Pop quiz. So kilowatt hours again is what you see on your electricity bill, right? So that's the magic number that we're tracking. So 5 kilowatts during a 2-hour period. How many kilowatt hours is that?
10.
Yeah. All right. Well done. All right. So 10. Now, if you have the easiest way to think about how much energy that is in terms of the solar production. So on a day like this, we have a lot of solar electric production, right? And that's going to help offset that 10 kilowatt hours that we used to provide this heat in the morning. And the easiest way to think of this is that it's called sun hours. And if you take this curve here and integrate it so that you add up all the heat, all the electricity that was produced during the day, and you say, okay, well, what if it? Wow, this is getting too complicated. But let's think about So the PV array on this house is 7 kilowatts, I believe, something like that.
7.8.
How much is it?
7.8.
Okay, so and the sun angle is still kind of low this time of year. So let's say that at its peak, it is producing 6 kilowatts. So if it was fully sunny out and it was producing 6 kilowatts, that means that the PV would have to operate for a little less than 2 hours to produce 10 kilowatt hours. So during the morning, what's happening is that because you use this heat for the backup heating element, the first chunk of the day, the first 2 or 3 hours or so of PV production, think of it as being spent on just recuperating what you just used for the heat. So we're not kind of back at net zero until sort of the middle of the day. Then everything we produce after that is contributing to an excess of power during the day. So now the question is, was it really necessary for this heat to ever turn on in the morning? So you have to think, well, what would have happened if the heat never turned on? When would this temperature start to naturally drift up? When would the temperature reach a point that's comfortable to the occupants? And then the question is, well, are the occupants willing to tolerate a couple degrees less in the morning as the building is naturally heating up? Are they willing to show up in a sweater and then take it off maybe at 10 a.m.? And the benefit, because you could see at 8 a.m. when they showed up, the building was at 73. It was already starting to overheat. But the temperature would not have been 73 at that point unless we turn this heat on. It probably would have been, I don't know, maybe 70 or something like 71, which technically speaking is cooler than what the occupants said they like. So it maybe would have taken an hour for it to go from 71 to 72, which is their magic number. But on the other hand, the building would not have overheated to 76.5 in the middle of the day. It may have stayed comfortable all day long. And so you could see the dynamics here. It's really, go ahead, Marika.
Can we test that on Sunday, the day after, like, because they're on Saturday, and Sunday the building's vacant. We could test that on Sundays.
Yeah, absolutely. Yep.
Monday and Monday.
Well, Monday, since the occupants aren't there on Sunday, it would be too hot on Monday, wouldn't it?
And you know, if you tell them, if you contact them and ask tell them that the temperature may be high 6 or 70 tomorrow morning, you know, tell them, okay, we're going to disable the heat to see what happens. And just tell them it's going to be 70 instead of 72 for a couple hours. They'll be fine with that.
Okay.
You know, so that you don't have to make a trip every time you want to check this. You know,
Okay.
they're willing, they're flexible enough to do that. It's just they were getting in the middle of the winter, they were, you know, when they have to sit there all day, they said they were cold. So, you know, this is different because the building's going to heat right up soon enough. So don't hesitate to ask them for a favor here or there. They've kind of signed up for that anyway. So,
Yeah.
Good.
yeah, so you can really see what happens. Today's such a good illustration. I mean, if they didn't open the windows, the temperature probably would have gone up. You can see the trajectory of this green line. It's going up to about 80. And then it would slowly drift down. And then it probably, depending on what the weather's going to be tomorrow, it may not ever reach that 72. And therefore the heat would never come on. But now, because the building has lost all that heat, which is fine. I mean, to stay comfortable, you have to do that. But now it's only gotten back up to 75.5, and it's probably going to drop below the heating set point. And so unless we disable the heat, it's going to turn back on in the morning again. And the question is that necessary? And it all depends, you know. Go ahead, Marika.
Probably now.
Right. Just one more question.
Oh, yeah.
Can we have the heating turned off during the weekend when it's vacant, so I can calibrate a baseline model without heating?
Yes, yeah, I can. You just have to tell me, and then I can. All I would do is the easiest way to do it is to say to the system, okay, the doors, the windows and doors are open, and that disables the heat.
Yeah, but I don't have the credentials, so I need to ask you a favor.
You have to ask me, yeah. Yep.
Yeah.
So just let me know. Let me know what time, and I can do that.
Do we need to get a permission from DNR to change this?
No. They've given me permission to change it.
Okay.
So, because when you make a request like that, the first thing I'm going to do is look at the forecast and see if it's going to get below freezing the following night.
To make sure it's safe.
Right, to make sure it's safe, yeah. And you know, I just noticed something interesting here. So look what happened today. The temperature dropped below the set point of 72 because the windows were open, and then the heat came on. Now, we're going to have to take a look at, now the heat should not come on if the building was, if open doors and windows mode was turned on by the occupants, because what that does is that's supposed to disable the heating and cooling systems when the windows are open. So this is a problem. Okay, this was wasted heat, wasted electricity. So I have this chart here which shows when, okay, you can see it. So this black line, oh, I see I see what happened. So they got warm. The black line indicates when open doors and windows mode was turned on. Okay, which again disables the heating and cooling. Because the whole idea, of course, is that if you're opening the windows, you don't want to have the windows open and the heat on at the same time. So they opened the windows at 1 o'clock, and then the temperature dropped right away because it must have been pretty cool outside, or maybe windy, which was forcing the cooler air inside. And it dropped all the way down below the 72-degree set point to 68. And then they probably got cold. They closed the windows and they did what they're supposed to do, which is turn off open doors and windows mode. But then the heat immediately kicks on
Yeah.
until it gets back up to 72. So interesting. I haven't seen this before. So what could have happened? I bet what happened is that they were warm. They opened the windows. They did what I asked them to do, which is turn this mode on. It started to cool down. They left to do something. By the time they got back, it was too cool. And then
Then we also want to know if the windows are closed, how soon the house will be raise the temperature without heating, right?
let's see. Well, the point here, the
Depends on
temperature
how-
really should never have dropped below. So one of two things, considering the limitations of the current control system, all right, the algorithm. One thing is for sure that this heat never should have turned on. I mean, the system operated the way it's supposed to, but in a perfect world, that heat should never turned on and should never have turned on. And so either the occupants should have closed the windows before the temperature got too low, or they should have left open doors windows mode on until the temperature went back above the set point. Does that make sense?
Yeah.
Yeah. So this is another thing that, of course, in a very smart house, right? In a very smart control system, I don't know how that would be implemented, but there's some way to come up with some scheme so that what happened today never happens, because that's a complete waste of electricity. And
You have to measure the oscillation time of during certain temperature,
Mhm.
so that you can predict if you open the window and outside is a certain temperature, how long it will take the system to
Yeah.
bring the oscillation back to the set point.
yeah, I mean, the most expensive way to do it is to have the windows and doors on motorized, so that the occupants don't have to, because the way we're doing it completely depends on them manually operating the windows and also manually turning on this mode. It's completely manual. So, you know, that's cheaper, but it's also more prone to things like what happened today, where you waste power. So it's all just a big trade-off. And I don't know, but that's interesting that happened today. So it's kind of,
Scenario, if this happen, you will lose money, so you will
Yeah.
not never happen.
but how much money are you losing? Are you losing so much money that it would actually pay for motorized windows? Probably not,
Yeah, exactly.
you know? So it's just sort of one of the limitations of a completely passive design, that it's never going to be controlled optimally. But, you know,
Is
it's
there
all
a term-
it's all trade-offs.
like,
All right,
where-
so that's kind of the story. You can see how this is an interesting problem to solve. And now the current control system, you know, if somebody's interested in taking this on and figuring out ways to make it more optimized, that especially, you know, whether or not it's going to be sunny the next day is a huge factor, because I've showed you why it's important, you know, so that's where, you know, predictive analytics comes in, and, you know, the system responds differently depending on what the weather's going to be the following day or even days in the future. And so obviously none of that is built into this system. So, but if anybody wants to take this on, then I can get into more details about how this is programmed so that you can start playing around with algorithms and things like that. So
Laura, you have the program, right?
I do.
So maybe you can, and Kaylin can work on some kind of programming strategy for this. Sure.
and another way we can do it is if, you know, if you guys come up with the algorithm and tell me exactly how you want me to program the data logger, then I can program it. You know, because
so we can know how to do that.
I remember that Laura was sitting behind Mike's back when he was programming the data logger, right? She was really interested in that. So maybe there is a way we can work on that.
Yeah. So, yep. So yeah, the key thing here, the way to learn the maximum amount from this, what's going on, is to open one of these charts and look for things that are not, it's not unusual, but when lines in charts change. So right here, okay, something happened, right? Why did this red line jump up by 10 degrees? And answering questions like that are the best way to learn about how the system works. And what's going on is that the heat turned on, the backup heating element turned on, and that happens when the house, the radiant floor in the house, that's programmed to come on at 72, under normal circumstances. The tank itself is programmed, its heating source is programmed to turn on when it gets down to 120. So if we zoom in here, we should see that, so this is top of solar tank. So solar tank here, you see the number, it's 119.8. So that was like the moment at which the system said, uh-oh, we're below the lower set point, and therefore we got to turn the electric heat on. So then after that happened, the heat stayed on until it reached 130, which is the point at which it's programmed to turn off. And these set points are in the, I'm calling it facility manager controls. So solar tank element turn on is 120 and then turn off is 130. So that's kind of how you would figure out what's going on there. And then of course there's all sorts of things changing here. So, but using these three screens, the controls interface, where I've tried to put all the set points in here, and then the interface that shows the layout of the system. So right now you can see there's no sun, 0 watts per meter squared. The collector is still at 90, and this is the solar hot water heater. It's still at 90 because it's still cooling down from the heat from today, right? But the pump that's circulating the water through the collector and into the tank is not operating because the temperature of the collector is 90, the temperature at the bottom of this tank is 135, and this tank is 124. So if this pump turned on, it would actually be cooling the tanks, So, and then those set points are also in here, solar collector loop set points, stuff like that. So right now the system is just kind of quiet. There's no water running. The radiant heat is not on. This tank is actually above 130, which means that whenever you see a tank above 130, that means that that was free heat provided by the solar collectors. And also it jumps above 130 when the heating element turns on, because that thing is really hot, but that's kind of an artificial heating. The heat is sort of circulating throughout the tank internally, and that's why these temperatures jump so quickly when the heating element comes on. It's because that heating element's very hot. So that's why. So by the way, the three red lines indicate top of tank, middle of the tank, and then bottom of the tank, which you can see right here. It's these three temperatures. And anyhow, I think I'm over my time, so. Hopefully that was helpful.
You were fabulous. No, this is really useful, and I think it also helps Kaylin make informed calls on the data, right? But I think we also have a little project for Laura and Kaylin. It doesn't have to happen immediately, but you can look at that and see with Sean on your side what the more improved control strategy would be for those particular morning times. Because, and then make suggestions for the occupants.
Yeah.
That one day when you started the conversation, I was not heating my house at all, and I don't have any thermal mass, and I hardly any insulation in the building, but it was 67 degrees in the morning still. So
Yeah.
those days we wouldn't need any heat ideally.
Right. Yep. And just so everyone knows, if you're ever really, the most important chart in this whole thing is annual energy balance, because the whole theme of these solar decathlon buildings is zero energy buildings, right? So this is when we started, June 15th, we started our official year of monitoring once everything started working well. And we reached, as the summer and early fall went on, we got up to 2,300 kilowatt hours, which is the equivalent of like $230. And then late fall, winter started, we started to drop precipitously because of the cold and the lack of sun.
It's turning around on the bottom.
What's that?
We're turning around.
Yep. So the question is, is there going to be another, so let's see, the lowest we reached was 2518, minus 2518. And then it's been mild, so it's going up. So the question is minus 2518 as low as it's ever going to go, or is there going to be one more, cold front coming through? But whatever. Eventually it'll turn up for good. But so question, I mean, if we're going to get back to, what we could find is that we only get back to minus 1 kilowatt hours. And that extra 1 kilowatt hour 1,000 kilowatt hours that we would have needed to get back to zero, that could have been made up by more precise controls.
And that's what we will go find out.
Yep. And this has been a pretty, the weather over the past 9 months has been warmer than normal, right?
Well, January was pretty similar than last couple of years. It was cold.
Okay.
November was warm. December, January were pretty normal. February has been warm.
And November was warm, right?
February was cold.
Yeah. Cold?
Yeah.
Well, February was cold. January was warm. February was cold. Sorry.
Okay. And November was unusually warm, right?
And you can compare, Kellen, you can look at the heating degree days from the utilities companies, and you can see what the comparison is with the years. Okay.
Yeah.
That's a good way to.
I know that because my February gas fee is pretty high.
Yeah.
Very. And for general comments about how much heat you expect to be consumed, you can look at the delta T with the dates.
Yep. Right? And that's so important. They often put that on the utility bill itself. Or they put the average outdoor temperature compared to last year and stuff. So.
Heating degree days and delta T is the key term for energy.
Yep.
If the building stays the same. I mean, obviously our values matter, but that's the variable.
Right. Yep. And this one is also good. I actually look at this one the most. Like just every day I check and make sure things are making sense to see. This is per day what the surplus or the deficit was. So that's the zero line there in the middle. And so you could see for a period of 2 months, at least 2.5 months, we never had a net positive day, and now we're having a lot more. So
yeah, now we have to make up what we lost over the winter.
Yeah. So, and this is actually the winter. There's not much you can do to optimize the controls. Because every day is sort of the same. The heat's needed, and now's the time of year when one day could be much different than the next. So there's more opportunities this time of year and also in the fall.
Cool.
So, all right.
Thank you.
All right, no problem. Okay. So Sean, you'll let me know if we're meeting next week or not, right?
Yeah, and Jake had a question that.
I don't remember.
Okay.
We're having spring break next week. Here.
Oh, okay. All right.
Yeah, we have spring break, but we might have a meeting, but more on the mobile diagnostic lab than on this.
Okay. Yep. All right. So maybe 2 weeks from now.
2 weeks from now, yes.
Okay. All right. Have a good spring break, all.
Perfect.
Okay.
Bye.
Have fun. Bye.
Take a weekend.
Right? Yeah.